PSGR Krishnamal College for Women are glad to welcome you all to the International Virtual Conference on Advanced Material for Sustainable Energy and Environment. This conference brings together scientists, professors, and researchers who are responsible for delivering sustainable and eco-friendly solutions through advanced science and technology. It provides a great opportunity for participants to share their recent experimental knowledge, research findings, and experiences in dealing with sustainable energy in the field of science. This conference features presentations of cutting-edge topics by international delegates. We are honored to have with us this morning our Secretary, Dr. N. Yashoda Devi, Professor Arumugam Mandiram, University of Texas, Austin, Professor S. Balasubramanian, Director, GRG-CAS, Dr. P. Sadasivam, Director, GRG-SMS, Deans, Dr. P. Meena, Associate Professor and Head, Department of Physics. We extend our warm welcome to faculty members, research scholars, and participants from various research institutes. Let us begin today's conference with a prayer song.
ஒரு நாளும் தளர்வரியா மனம் தரும் தனம் தரும் கல்வி தரும் ஒரு நாளும் தளர்வரியா மனம் தரும் தெய்வ வடிவும் தரும் நெஞ்சில் வஞ்சமில்லா இனம் தரும் நல்லனையெல்லாம் தரும் நல்லனையெல்லாம் தரும் அன்பர் என்பவர்க்கே கனம் தரும் பூங்குழலாள் அபிராமி கடை கண்களே
We now request our Secretary, Dr. N. Yashoda Devi, to deliver the welcome address. Ma'am, please.
Good morning. It is my great pleasure and honor to welcome you all for the inaugural ceremony of International Virtual Conference on Advanced Materials for Sustainable Energy and Environment, ICAMC 2022. Energy is essential for development, and sustainable energy is essential for sustainable development. Our quest towards the sustainable development of the world by means of advanced green and renewable energy resources goes on increasing day by day for the betterment of our lives, our economy, and our planet. Mastering the development and use of sustainable energy is of great significance to researchers and students, and its deep understanding can surely be achieved through the eminent people who have graciously accepted our invitation for this conference. I am very happy that the Department of Physics is conducting such an important conference, which is really essential at this point of time. Respected Chief Guest of the function, Professor Arumugam Mandiram, Professor S. Balasubramanian, Director, GRG School of Advanced Studies, Dr. Sadasivam, Director, School of Management Studies, Deans, faculty members, research scholars, and participants from various institutions, I extend a warm welcome to you all. I take this opportunity to express our gratitude to Professor Arumugam Mandiram for accepting our invitation to inaugurate the conference. Thank you, sir, for sparing your valuable time. Professor Mandiram, who is currently the Director of Material Science and Engineering Program of University of Texas, Austin, completed his PhD from the Indian Institute of Technology, Madras in 1980, and carried out his postdoctoral work at the Indian Institute of Bangalore between 1981. And then he worked as a lecturer of chemistry at Madurai Kamaraj University for 4 years. In 1985, he joined as a research associate in the laboratory of Nobel laureate John B. Goodenough at the University of Oxford, England. He then joined the Material Science and Engineering Division of University of Texas, where he has served in various capacities from research associate to professor of the department. Professor Mandira has published more than 900 journal articles and has 84,000 citations with an H-index of 141, and he has 16 patents to his credit. A great achievement, excellent research work. Hats off to you, sir. Professor Mandira has received various awards and honors for his excellence in the field of batteries and fuel cells. To name a few, he has received the Battery Division Technology Award from the Electrochemical Society, Web of Science Highly Cited Researcher Award, International Battery Association Henry B. Linford Award for the distinguished teaching from the Electrochemical Society, Distinguished Lectureship Award from the School of Chemical and Biology Engineering, Seoul National University, South Korea, Distinguished Alumnus Award from the Indian Institute of Technology, Madras, and the Battery Division Research Award from the Electrochemical Society. He delivered the 2019 Nobel Lecture in Chemistry on behalf of the Nobel Laureate in Chemistry, John B. Goodenough. We are really fortunate to have such a world-renowned scientist amongst us today to deliver the inaugural address. Thank you, sir, and we extend a big welcome, warm welcome to you. This conference is a good time to refresh our minds and discuss the development and stages of next generation clean and green energy devices with the eminent scientists from various prestigious institutions. I can see a blend of extraordinary and smart researchers who have made this way possible. It is always a pleasure to see the quest of knowledge among students of the science community. So with these few words, with a high round of applause, let's request Professor Mandira to grace the conference with his inaugural speech. Welcome to you, sir. Welcome to one and all. Thank you.
Thank you very much. Can you all hear me? Can you all hear me well?
Yes, sir.
Okay, thank you very much for the invitation. I'm pleased to see that such conferences are happening here, particularly in Tamil Nadu, Coimbatore. I think as we move forward, energy is going to be the greatest challenge facing us. And I think it's important that we have proper education. That's where it starts. So the energy technology involves, or it cuts across several fields. It starts with chemistry and physics, then material science, various disciplines of engineering, mechanical engineering, chemical engineering, electrical engineering, as well as other disciplines. So it is important that we have the necessary early education for the students so that they can choose the right career and contribute to this field. My lecture is coming later, right?
Yes, sir.
Okay. This is just an introduction, right?
Yes, sir.
Okay. So
We now
if you consider the population right now, the population is similar both in India and in China, around 1.4 billion. The US population is 1/4 of that, around 0.35 million. But the energy use, if you take, China uses about 24% of the global energy use. The whole world you take, China uses 24%. India, similar population, but we use only 6%. US population is 1/4 of the population of India and China, and US is already using 17% of the global energy. So if you consider that if India catches up with China, then we need 4 times more energy than what we currently use now. And if India catches up with the US, we will need at least 10 to 15 times more energy than what we use now. You can think of getting energy from fossil fuels, coal, gasoline, petrol, and other things, but that is going to create more pollution. Actually, pollution is the major concern to drive all these clean energy technologies. So solar and wind are the solution, but then they are intermittent. There are cloudy days and sunny days. There's day and night, and wind wants to come when it wants to come. So that means storage is very critical. We have a lot of solar cells now. Right now, the bottleneck is how do we store economically and efficiently and utilize the electricity collected from solar energy and wind energy. So that is a struggle. For that, battery technologies are the most viable option. And for transportation, the vehicle is all over the world. There is no containment. It is polluting everywhere. For transportation, again, battery technologies are the most viable option. One can think of fuel cells. Yes, fuel cell is an energy generation device. You do not need electricity to charge as long as you have a hydrogen cylinder or methanol or ethanol. It can provide energy, but it is prohibitively expensive. Platinum use, hydrogen production, all those. So for the time being, fuel cells are not going to make it. Batteries are the most viable option, both for electric vehicle as well as for grid storage of the electricity produced from wind and solar. So I really look forward to the various talks in this conference. As I said earlier, it will be a good education for the students and the faculty members who teach. Thank you very much.
Thank you, sir. We now request our secretary, ma'am, to release the souvenir and to give the first copy to Dr. P. Meena, Associate Professor and Head Department. Ma'am, please.
உங்களுக்கு தான் தெரியும் தானே இந்த பாட்டு பிஹெச்டி தான் தச்சிங்க
இல்லையா அபிராமியோட சாங்
அது விநாயகர் சாங் பாருவாங்க
இந்த பாட்டா
இல்ல
Thank you, ma'am. Thank you, sir. We now request eminent Professor Armuga Mandiram, University of Texas, Austin, to deliver the inaugural address on sustainable battery chemistries for a cleaner environment. So please.
Okay, let me share my screen. You have to enable me to share my screen.
We are doing it, sir.
Okay, it is still not, it says host disabled participant screen sharing.
We are working on it.
Okay,
Sharing.
yeah, I got it. Thank you. Do you see my slide?
Yes, sir.
Okay. So first, I congratulate the college management and all the faculty members involved for organizing such a conference. And particularly when Priyadarshini invited me, I was very happy for one particular reason, that these days we talk a lot about DEI. I don't know whether you all talk about that in India or not. DEI means diversity, equity, and inclusion. So because it's a women's college, I was very pleased to accept the invitation. And even though it is now going to be 10 o'clock, 10 p.m. my time, I was willing to give the talk. I'm an early riser. I wake up every day at 5 a.m. and go to bed at 9:30 p.m. But again, I want to tell you that I'm very, very happy, and I really congratulate you all for taking the steps to organize such a conference. So my talk, not all of you are working on batteries. So I have arranged my talk in such a way to be very educational. So at least up to the first 10 slides, it will be very educational. So you will know what are the important things and how do we handle them. So as I mentioned earlier, this gives the global energy consumption. And you can see here the year 1800, now 2000 something. So as we move forward, the energy use is skyrocketing. Actually, the energy use is expected to triple by the year 2100 compared to what we have now, 3 times more than the numbers you see here based on moderate economic and population growth. And I mentioned already this, China 24%, 1.4 billion population, India similar population. Actually in India, we may have more population than China. Maybe we are not counting everybody, but they are similar. You can see US population is 1/4 of that. And the energy use numbers are given here as you see. So if we catch up with China and then US, India will need enormous amount of energy, an order of magnitude, higher amount of energy than what we use now. So that's the challenge. So how are we going to manage? We already have high prices for the gasoline or petrol, and we use more. Demand goes up means more cost. The energy use again here, if you look at it, it is dominated by fossil fuels, coal, oil, and natural gas. And there is a finite supply. People may argue, okay, there is no problem. We have plenty of those. What do you worry about? One sector of people can talk about like that. Another sector of people may think, no, it is going to stop, or we are going to have a problem with these resources after some time. But whatever it is, the most important factor is when we use coal, oil, and natural gas, they are going to create a lot of air pollution. Actually, that is the major challenge. That's what is driving everything for clean energy technologies. So what is the solution? Before that, this is a chart from Rice University. Actually, I should have written here, but not written, from Rice University, Smalley Institute. He was a Nobel laureate for the carbon C60 and others. So if you look at here, what are the top 10 problems for humanity during the next 50 years? Energy is on the top. Next, water. Next, food. We know these three are very important. And if we have a problem with this to produce, then we are going to have a big environmental impact that will have health consequences. And then if we have a problem with the first 3 and 4, people will become impatient. If there is no food, no water, there will be poverty. Actually, this is from that Smalley Institute at Rice University. But I think it's a chain reaction. That's what I'm trying to point out. If you have a problem with the first 4, that will certainly lead to poverty. And if you have poverty, people will become impatient. There will be terrorism and there will be war. People will be fighting with each other to get more resources. If that happens, number 6, that will automatically lead to a lot of disease. If those things happen, then education will be lost. If education is gone, democracy will be lost. That means ultimately people will die with all this. So this is a very good slide to indicate that we need to clearly address the challenge we are facing: energy, water, and food, particularly energy on the top. So what is the solution? The solution is that is the renewable energy, solar and wind. But they are intermittent, as I pointed out earlier. So we have to collect the electricity from them during the day, and then when the wind is blowing, and then use it when we need. And the use is different during the night and in the daytime. So if we store it, and we can use whatever way we want. So storage is the bottleneck right now. There are solar cells, that's not a problem, but storage is a big bottleneck right now to use them efficiently and economically. You don't want them to cost more than the fossil fuels that nobody is going to use. People may not care too much about pollution. So cost is a big driver. So what is the option for storage? Battery technologies are the most viable option, near-term option at least. But they also have their own issues. That's what I'm going to talk about. Cost is an issue, energy, how much you can store, charging time is an issue. You are already having problem with your laptop or cell phone. You want to charge in 5 minutes, but you cannot. I will explain why. And then how long you can use it before you replace it. And am I going to have any safety problems? So they have their own problems. And all of those problems are linked to severe material challenges. And for transportation, I already explained, uncontrolled pollution everywhere we drive. So electric vehicle is a solution. And then again, battery technologies are the most viable. Fuel cells will be much preferred because that is an energy generation device. Battery is an energy storage device. Basically, you store electrical energy from an electrical outlet as chemical energy in the battery, and then you use it when you need it. Fuel cells are not like that. You have a hydrogen cylinder or methanol in a tank or ethanol in a tank or even natural gas in a tank. Then that with the air can undergo a reaction to produce water or carbon dioxide if you use natural gas. And the free energy change in that reaction is taken out as electricity. Unfortunately, they have many more problems than batteries. Cost is prohibitively high, so we are not ready to use those technologies. Although the hydrogen is coming more and more now, US government is going to put $7 billion out of the infrastructure legislation passed. And for battery technology, there are $6 billion B. That means 1,000 million, right? So $6 billion. So that is what is going on everywhere. So with that, let me first explain how a battery works. As I said earlier, chemistry and physics is the starting point. If you know good chemistry and physics, you can do good engineering. This is something Professor Goodenough, the Nobel laureate, used to tell me. They used to call me here Ram. It's hard for them to call me Armugam Matiram, so they used to call me Ram. Then he told me long back, 30 years back or 25 years back, Ram, if we know good chemistry or physics, preferably both, you can do good engineering. And I completely agree with that. To do good engineering, you need not study engineering. If you do good chemistry, if you have good chemistry knowledge, good physics knowledge, you can use those to make good engineering products. So let me explain this a little bit. A battery will have three components: a negative electrode called anode and a positive electrode called cathode. They will be separated by an electrolyte. And what is the function of anode and cathode? The anode and anode, they will store charge in the form of ions. I'm taking lithium ion batteries as an example. So during charge discharge, the lithium ions are moving back and forth. So when you charge it, you store the lithium ions in the electrode. The electrolyte is separating the anode and cathode. It's in between. And the electrolyte should allow charge transfer only in the form of ions. Or in other words, the electrolyte should not conduct electricity or electron. It should allow charge transfer only in the form of ions, you see, and the electron should go through the external circuit. So let me start here. When we charge, lithium ions go from the cathode to the anode, as you see. And when you discharge, exactly the opposite will happen. So when you are moving the lithium ions from the cathode to the anode, you are moving positive charges. That has to be compensated. So that compensation is done by the electron moving from the cathode to the anode through the external circuit. So basically, you have ions and electrons, but they go in different route, different road, and they come and meet here, and locally they neutralize the charge. So that's what is happening now. So that is pictorially what is going on. Charge, you do that when you use the cell phone, it is going and coming back here. So that's nice. But how do we understand the chemistry and physics? What is really happening? How are we storing the energy and getting out the energy? So for example, this is the band diagram, the same cathode in the other diagram. I'm drawing in the form of their band diagram or energy diagram. So this is the redox energy of cathode. That is the redox energy of the anode. Or from a physics point of view, you can call it the Fermi energy of the cathode and the Fermi energy of the anode. But that is only to a first approximation. There are a lot of other factors which will influence the voltage by more than 1 volt. Therefore, you cannot simply say Fermi energy as you will talk in physics. You have to consider other terms. So redox energy is the most appropriate term. So let this come back. So during charge, now we are going to charge. So during charge, we are pulling out lithium ions, and that is we are putting into the anode. At the same time, the electron is put into the anode. So during discharge, so that means during charge, you are using electricity, pumping the electron from a lower lying cathode energy level to a higher lying anode energy level. So that's how you store electricity in the form of chemical energy in the materials. So that is not spontaneous. Delta G positive for that, because you are pumping the electron from a lower energy to a higher energy. So that is non-spontaneous, that is charging, and you are pushing it by supplying electricity from an electrical outlet. During discharge, the electron falls from a higher lying anode energy to a lower lying cathode energy, and that is spontaneous because there is a decrease in free energy, and that free energy change is related to the voltage. E here refers to voltage, F refers to Faraday constant, and that can be obtained from Avogadro's number and multiplying that by the charge on the electron. N is the number of electrons involved. So this is what basically happening as far as the physics is concerned. Now, I also want to, it looks very simple. Yes. So the energy density, that is the user time. How long I can use my cell phone or laptop, or how long I can drive before I have to charge my scooter or electric car is the energy density. That is what that determines, that's the user time. So that depends upon two factors: cell voltage times amount of charge we store in the material per unit volume or per unit weight. So that means to maximize the voltage, I have to keep the cathode energy as low as possible, anode energy as high as possible, because the cell voltage is the difference between this energy and this energy. The redox energy is in the anode and in the cathode. So that means keep it as low as possible, keep this as high as possible. But there is a constraint. They have to lie within the band gap of the electrolyte. The electrolyte is also a chemical, solvent and salt. They will have their own energy level. HOMO means highest occupied molecular orbital. You have electrons here. LUMO means lowest unoccupied molecular orbital. So these two energy, cathode energy and anode energy, has to lie within the band gap. Why? Let's imagine a situation. I am too greedy. I want to have a cathode which has its energy somewhere here, below the HOMO. If it is during charge, instead of pulling out the electron from the cathode, I will be pulling out the electron from the HOMO of the electrolyte, because my cathode energy is here, my electrolyte energy, occupied electrons in the electrolyte are somewhere here. So we will always pull the electron from the highest occupied band or molecular orbital. So the electrolyte will undergo oxidation. The electrolyte should not undergo any oxidation or reduction. Oxidation means losing electron, reduction means accepting electron. Chemistry. So you cannot do that. You should allow only the charge to transfer in the form of lithium ions. Same way, if the LUMO is down and if the anode is above the LUMO level, then when I charge, instead of putting the electron into the anode, I will be putting the electron into the LUMO. So electrolyte will be reduced, which is not. You cannot do that. Then electron is leaking internally like that within the system. Let me put my camera. I'm sorry. I forgot. Sorry about that. You see me now? Okay. So that's the constraint. So they have to be always within that. That means we are limited in voltage, even though you may have a cell, you may have appropriate materials that may have 5 volt, but we can't use it right now. We do not have lithium ion batteries, which are more than 4.2 volt. Each cell can give you only 4.2. Stuck. Okay. Each lithium ion cell can give you only up to 4.2 volt. If you go more than that, the electrolyte oxidation will happen. The cycle life will go down. That means instead of using your cell phone, say 4 years or 3 years, it may go down pretty fast in 6 months. A laptop same way. So the charger will not allow you to charge more than 4.2 volt. Okay, so we have done that. Now, what is so the other factors, amount of charge stored, that means how much space I have here and how much space I have in this material per unit weight, per kilogram, or per unit volume to store lithium ions in the case of lithium ion batteries, or sodium ions in the case of sodium ion batteries, or magnesium ions in the case of magnesium ion batteries. So by the way, I illustrated this with lithium-ion batteries. If it is sodium, you will have a similar situation, and then sodium ions will be moving back and forth. If it is a magnesium-ion batteries, magnesium ions will be moving back and forth. If it is proton-based, then proton will be moving back and forth. Now, lithium-ion batteries are not the end of the world. There are a lot of other batteries. For example, I have shown some here. Lead-acid battery, each one of your car or a scooter or other things, the vehicle you use, they all have lead-acid because that's what we use to start the car and light and other things. And we also have nickel cadmium and nickel metal hydride. Those of you old enough, in the 1980s, 1990s, we used to use even nickel cadmium or nickel metal hydride in the cell phone and laptop in the 1990s, because lithium-ion batteries were commercialized, first commercialization in 1991. Now they have been almost replaced by lithium-ion batteries. So why we are replacing with lithium-ion batteries? The reason is all these three batteries, lead acid, nickel cadmium, but nickel metal hydride, they all use water-based electrolyte. Lead acid battery uses sulfuric acid, that has water. Nickel cadmium and nickel metal hydride uses potassium hydroxide, that has water. When you have water in the electrolyte, the band gap I was talking about is narrow. You cannot have more than 2 volt. So voltage is just less than 2 volt. When you go to lithium-ion batteries, water is an enemy. You have to use non-aqueous, water-free, even parts per million levels of water cannot be present in lithium-ion batteries. Because you have non-aqueous solvent, not water, the band gap of the electrolyte is widened. So I'm able to keep the cathode energy as low as possible and the anode energy as high as possible, but not more than 4.2 volt. But that is a lot better, double the voltage compared to any of these batteries. So you can see here, voltage is doubled. That means user time is doubled if the amount of charge stored is assumed to be similar. So that's why all the action is on lithium-ion batteries. So now you see already the complication. Electrode, electrolyte, and then how do their physics-wise, how their energies, relative energies are located with respect to the electrolyte. So it's complicated, even though it may look simple. When you use the battery, it's very complicated. I'm going to tell you more complication now. Now, how did this all happen? All the lithium-ion battery technology we use right now were all developed in the 1980s. Nothing else has changed. Chemistry is still the same. Same chemistry happened in 1980s. 40 years later, still we are using the same thing. The only thing which has happened over time during the past 40 years is the engineering has changed, making current collector thin, separator thin, making better electrode processing so that you have more accessibility, more utilization like that. But as far as the materials are concerned, basic chemistry, nothing changed. I will show that later. So now, little bit of history. These were the 3 people who were awarded the Nobel Prize in 2019. So the technology was first done by Professor Whittingham, Stanley Whittingham. He's from England, British. So he did his PhD at Oxford. After finishing his PhD at Oxford, he went to Stanford University to do postdoc. Then after that, he was employed at Exxon Corporation in the United States. And when he was at Exxon Corporation, he demonstrated the very first rechargeable lithium batteries by taking lithium metal as the anode and titanium sulfide as a cathode. Titanium sulfide has a layered structure somewhat similar to this. Not exactly similar to this. So that was the very first technology that was published in Science in 1976. But in a sulfide, it's very simple, basic science-wise. You know, sulfur has 3p orbital, oxygen has 2p orbital. We consider sulfur 3p orbital. That energy is here. So your cathode energy cannot be lowered below the top of the sulfur 3p band. That means If you use a sulfide cathode or a selenide cathode or a telluride cathode, your voltage is always less than 2.5 volt because you cannot lower the cathode energy below that. That is one problem. Second problem, in the 1980s, these cells were made with this kind of technology. They were putting it in the market and there were fire hazard. So they put it in the market. Then they were recalling the battery. Then business closed. That's what the two problems. They were almost, okay, this thing is not going to work. Professor Goodenough, you see here, he's a physicist. Stanley Whittingham is a chemist. Professor Whittingham is a physicist. And he was working at Lincoln Laboratory, Massachusetts from 1952. He was born in 1922, July 25th. And he will be 100 years old this year on July 25th. So we are going to have a big one-day symposium we are organizing at the University of Texas at Austin. He has not still retired. 100 years old. He will be in July. In India, I know you cannot, everybody has to retire, I suppose, at 58 or 60 or 65, something like that. In the US, you cannot ask people to retire based on age. So anyway, so he's a physicist. He was working at Lincoln Laboratory in Massachusetts from 1952. He was working on all kinds of oxides, not for batteries, but for magnetic applications. The very computer memory, RAM memory, RAM memory, random access memory, was developed by his group at Lincoln Laboratory. He was already recognized for that. So he always worked with good chemists. He's a physicist, but he worked with good solid state chemists. So he was very familiar with all the oxides, their structure, what do they do, bonding, covalent bonding, ionic bonding, very familiar. And he also knew how the energy levels of some of these things change. So very simple. Now it may look simple. He knew, okay, you have voltage limitation and you have a problem using lithium metal. I know something, lithium cobalt oxide, that has a layered structure like here. And also, if I go to an oxide instead of a sulfide, the oxygen 2p band lies at a lower energy than sulfide 3p band. Therefore, I will not have this kind of block. I can lower my cathode energy, not somewhere here, I can go all the way down to the top of the oxygen 2p. So suddenly, the voltage could be increased by using an oxide cathode instead of a sulfide cathode from less than 2.5 to 4 volt. Yeah, good. Energy density is increased, number one. Number two, you have a problem with lithium metal because that is forming dendrite and making a hole across the separator and connecting the anode and cathode. Therefore, you have the current flowing internally. Don't worry, I will have lithium in my cathode. So I will choose my cathode like lithium cobalt oxide, lithium already has. I will first charge and put the lithium ion into here like I was showing in the other diagram. Very simple, that made it. Then Yoshino Akira in Japan, he was working on carbon-based materials as anode. So as soon as he saw lithium cobalt oxide, he coupled the carbon anode and lithium cobalt oxide, carbon as a host, and then he demonstrated the very first lithium ion technology. And then Sony used that patent and they announced commercialization in 1991, and that's what we have here. And since 1991, same chemistry, but only thing is engineering is changing. If you want to know more about this, I was finally able to write an article in 2020, published in March. I looked today before this talk. This is an open access journal. If you put in your Google right now, the title, here reflection on lithium ion battery cathode chemistry right now, you will get that article, full article, open access, anybody can get it. So I checked now, you will know how the history happened and also the chemistry and physics associated with these materials. That's a very good article for teaching. And some of the things I'm doing here, actually I'm teaching in my class. That's what I'm doing here today. So this article has already been accessed 84,000. 84,000 people have accessed this article. It is not 2 years yet. Next month, it will be 2 years. 84,000 people. And I don't know who those people are, but that's amazing. I've never seen anything, 84,000. It keeps increasing. Pretty soon it will be 100,000. Then I have to celebrate it. But anyway, if you are interested, look at that article. It will be very educational and you will know all this. Now, good. Now, okay, we got it. Battery looks simple. Is it simple or it is complicated? It's both. It's simple and it is complicated. We have to consider various parameters. You see here band diagram, structure, chemistry and physics. I'm a chemist. I was teaching chemistry master's students at Madurai Kamaraj University postgraduate extension center in Palangotai for 4 years. I thought my career is all over. But fortunately, God was kind enough. I was able to go to Oxford and everything changed. Anyway, energy density, how much energy you can store per unit volume, per unit weight. How fast I can charge, discharge, power density. How long I can charge, discharge, cycle life. Am I going to have safety problems? Am I going to have toxicity with the material or the processes I use? What is the cost of the material? Actually, cost is everything. If you have stored more energy in a cell, instead of making 100 cells, you can make 50 cells. I save money. So everything is cost. If it cycles long time, I do not have to replace it. I save money. If safety is not a problem, I do not have to break my head. I do not have to worry about somebody will sue my company when the car is on the road. So everything saves money. And which parameter I pay more attention depends upon the application. And which battery technology I'm going to use again depends upon the application. First, for portable application, laptop and cell phone, user time is the most important one. Cost you don't care because it's a small battery. Life also you don't care because you have iPhone 7, 8, 9, 10, 11, 12, 13. They want you to keep on buying. So 3-4 years you throw away, you get another phone. So it's not a problem. Electric vehicle, little bit larger battery, energy density is still important, driving range. It may not be that important for India, but Western countries, they pay a lot of attention to energy density. So that means slightly larger battery. So cost becomes important. Car is on the road, safety becomes important. Because it's a little bit more expensive, $10,000, $15,000, life also becomes important. Grid storage, large, big battery. It is going to be in the ground somewhere in your college campus, and it can power the whole college campus or the whole Coimbatore city, right? So cost, it's a big battery, millions of dollars. Cost is very important. You don't want to replace it very often. You cannot. You have to use 10, 20 years. So life is important. And of course, safety is important. It's not on the road, but big battery, if it catches fire, you don't want to have fire immediately coming to your building or to other houses in the city. So you kind of see there is not just one technology we can think that will take care of everything, not necessarily. For grid storage, particularly cheaper technologies are necessary. So I told you which parameter I have to pay depends upon the application. Which battery I use also depends upon the application. Of course, we need fast charge. That's another parameter. And we don't have that. If you do fast charge, it will degrade faster, it will fail faster. And then India, Coimbatore is a very nice place. I have never been there. Maybe next time when I visit, I will visit. But if you consider Delhi, too hot in the summer, too cold in the winter, so the battery should be able to operate in the auto rickshaws for those conditions. So that's actually temperature tolerance is very critical for India. So that's why for India, there are different battery technologies. You may have to choose the appropriate technology. So with that, how all these parameters I'm talking about, how are they related to the physics and chemistry. I keep mentioning all these parameters are severely controlled by material challenges. So why do I say that? The energy density is a product of voltage and degree of how much ions we can store in the material. That depends upon the structure. You have to use 3D transition metal ions rather than 4D transition metal or 5D because they are heavier. Power density, charging time, or low temperature performance depends upon the electronic conductivity of both the anode and the cathode, not the electrolyte. The electrolyte should be an insulator, and the ionic conductivity of the two electrodes and the electrolyte. That's what determine the power density or all these parameters. Cycle life is determined by, or battery life is determined by how reversible these reactions are. Can you do it repeatedly? How stable the structure is when you keep on doing. Thermal stability or fire hazard or safety depends on whether the anode is going to grow dendrite during charge or whether the cathode is going to release oxygen and your electrolyte, liquid electrolyte, organic liquid electrolyte is flammable. Actually, for safety, all the three guys are responsible. The anode, cathode, and the electrolyte. But who is starting? The guy who initiates the anode, graphite anode. If you charge fast, instead of lithium going inside, it will deposit on the surface. Unfortunately, when it deposits, it does not deposit smoothly. It deposits like a needle. That's called dendrite. Once you have a needle like kundusi, then it will make a hole on the separator. Then it will internally connect from anode to cathode. So an electron will not flow through the external circuit. It will be flowing internally. Heat, current flows internally. Heat, temperature goes up. As soon as it goes up, the cathode guy, cobalt oxide, okay, I will release oxygen because cobalt 4 plus is not very stable. Nickel 4 plus is not very stable. Oxygen comes, the liquid electrolyte is there, organic electrolyte, that is like gasoline. Okay, we caught fire, I will help you. That's what is happening. All the three guys, they mess around. Environmental impact, toxicity, that is materials, which material you use, and the processing. Cost, like I said, everything. So at least you see here how the 6 parameters I talked about, how they are related to the fundamental chemistry and physics of the materials. Now, I've listed some of the battery technologies here. Lithium-ion batteries are on the top. Sodium-ion batteries similar to lithium-ion batteries, but you will always have a little bit less energy density than with lithium-ion. But sodium-ion has a big advantage. What is the advantage? Sodium is plenty. Fortunately, India has ocean, the sea around. There is a lot of sodium in the sea. So you can get sodium from there rather than worrying about lithium. So cost is a big advantage, particularly for grid storage. Sodium-ion batteries are particularly very attractive. Multivalent means magnesium 2 plus or aluminum 3 plus, very appealing because if I store one lithium or one sodium, I store only one charge. If I store one magnesium, one zinc or one calcium, I store 2 charges. Wonderful. If I store one aluminum, I will store 3 charges. So that means I am tripling the energy density from aluminum or doubling the energy density with magnesium and zinc compared to lithium or sodium. Wonderful. But 2 or 3 problems. You see the redox energies here. Lithium is way up in the top. Sodium is here, a little bit less voltage. If you go to other zinc or aluminum, magnesium, they will have lower voltage when you use as an anode. So voltage will be decreasing first. Second, these ions we saw earlier, when you use them, they have to move through the lattice. It's a crystal, right? You have material through which the ion have to move. Lithium and sodium monovalent, one charge they can easily move. When you have 2 or 3 plus charges, they will have a lot of electrostatic repulsion. With the manganese 4 plus or cobalt 3 plus, they will have a hard time to diffuse. So they will have poor ionic conductivity. And also there is no good electrolyte right now. So almost, as far as I am concerned, these are not going to be very useful as far as the practical batteries are concerned at the moment. All these are using mined metal ion cathodes, iron, cobalt, nickel, manganese. They have to be mined. So if you use sulfur as a cathode, then you do not need any manganese, cobalt, nickel, nothing. And that can be coupled with any of these, lithium or sodium or magnesium working ions. But sulfur is an insulator, electronic insulator, poor lithium ion conductor. Remember, I mentioned here, the electrodes should have good electronic conductivity, good ionic conductivity. That is pretty bad, unfortunately, with the sulfur because it's an insulator. And also sulfur dissolves, goes from one electrode to another electrode. It's a problem, messing around. But sulfur stores 10 times more charge than the other cathodes. So you can store a lot of energy, but unfortunately it has the other problems. Yeah, metal air battery means you use air as a cathode. That is good because you don't need any mined metals. But when you see non-aqueous batteries, for the air, if you use oxygen has double bond O, double bond O, you have to break the bond. You need a good catalyst, platinum, for example. And that catalyst will also decompose the non-aqueous electrolyte. So non-aqueous metal air batteries are almost dead for practical application. Aqueous metal air batteries like zinc air battery, aqueous solution, that can be used. There are a lot of development, particularly for grid storage. Redox flow battery means the lithium ion technology right now is the electrodes are solid, electrolyte is liquid soaked in a separator. That's what we have right now. Redox flow battery means your electrodes are also solution. So you can store them in a big tank. So you can store a lot of energy for a longer time. But then, because they are liquid chemical, the chemical on the anode side will go through the cathode and the cathode side will go through the anode. That is called chemical crossover. That will bring down the efficiency. That's a problem. But particularly that is very well suited for grid storage. But unfortunately, the serious chemical crossover problem. All solid state batteries, that means your electrode is solid. Your electrolyte is also solid. So that is the holy grail of whole battery technology. But the issue is, when you have two solids like this, they are not wetting each other. So how am I going to transfer the lithium ion from this electrode to that electrode? They will have a hard time. When you have one solid and you have a liquid on the surface, it is wetting. So the lithium ion or sodium ion transfer from the solid electrode to the liquid electrolyte or from the liquid electrolyte to the solid electrode is easy because it's having good wetting. Interface is good. With the two solids, interfacial charge transfer is killing everybody. It's a problem. You cannot charge, discharge fast. And all the solid electrolyte known are ceramic oxides or sulfides. How they are brittle, they'll break like glass. So how am I going to manufacture large area ceramic solid electrolyte? If it is a polymer solid electrolyte, that will be good, but unfortunately, we do not have any polymer electrolyte that can have acceptable lithium or sodium ion conductivity. So that's a challenge. So this kind of tells you the whole battery, different battery technologies we can think of, but right now, there is nothing to beat lithium ion batteries as far as the portable application and electric vehicles are concerned. That's where we are, but things can change as we move forward. Nobody knows. We don't know. When I was doing research in the 1980s and 1990s, we never thought the materials we do will be used somewhere. Amazing. Now, right now, the whole lithium-ion technology is based on graphite anode. That's the only anode. And for cathode, three possibilities: a layered oxide, a spinel oxide, a polyanion oxide. Spinel means spinel structure. That's why it is called spinel. So these three were, you see here, they all have some 200 or 150 amp hour per kilogram charge storage capacity. If you take sulfur or oxygen, they have 10 times more charge storage capacity than any of these. That's why a lot of interest, but a lot of problems. You see, the scale is breaking here. Hundreds, scale broken. These are thousands. Big change, order of magnitude change. Now, the current technology is based on only these three kinds of cathode. They are all developed by Professor Goodenough's group in the 1980s, both at the University of Oxford in England and at the University of Texas at Austin. So a little bit of history. Again, if you read this paper, you will know. It involved 3 visiting scientists from 3 different parts of the world. I put the countries here, not students. Mishishima came from Japan. He had a job there. He came from Japan, worked with Goodenough on layered lithium cobalt oxide. Then he left. Michael Thackeray came from South Africa. He had a job there. He worked at Oxford. They developed lithium manganese oxide spinel cathode. He left. I went to Oxford in 1985 November when it was beginning to be bitterly cold, going from Tamil Nadu. Then we started working on a series of polyanion cathodes. Polyanion means, here you see simply anion is oxide, anion is oxide. Here you have a molybdenum MoO4 or WO4 or SO4 sulfate or PO4 or SiO4 silicate. So these are complex anions, polyanion they are called. So now let me say a little bit about this. I pointed out earlier, when you go from sulfide to oxide, the voltage is increased from less than 2.5 volt to 4 volt. And with the same ion, when you go from an oxide to a polyanion, the voltage again increases by more than 1 volt. So from here, from these oxides to these, the voltage increases because the polyanion units have more covalent bonds. So the iron-oxygen bond will become less covalent, more ionic. So it is not raised that much as an antibonding level. So it is lowered. So the voltage increases. I think it's too hard for you to understand if you do not have the background. But anyway, the chemical bonding has a big influence. The chemical bonding changes can change the voltage by more than 1 volt. Voltage is money. Because the more voltage you get, the more energy you store. Now, the interesting things here. So they left, right? He left, then I came. I am the only one. We came together 1 year later from Oxford to UT Austin. We continued, and the polyanion cathodes were developed furthermore at the University of Texas at Austin. We talk about a lot about sustainability these days. You see here, cobalt is more expensive. Manganese is less expensive. Iron is the cheapest 3D transition metal you can think of. The cost reduction is already built in. 80s, you see here, 1980s. And then safety. Cobalt releases oxygen very easily. It's not good for safety. Manganese is better. The polyanions, these X, they will hold the oxygen very tightly. They don't lose oxygen easily. That's the beauty. So the polyanion has the ability to increase the voltage by more than 1 volt, as well as better thermal stability, better safety. That's the beauty. Also, the polyanion now has the concept, has variety of materials, a very broad family. So as I mentioned earlier, these are the 3 series or 3 family of cathodes developed in the 1980s concept, and we are still with those. Nothing has changed. Everything else is kind of here and there, but practically not used. Now, what do we do? In my lab, all along, this is my very first beginning. You see, already sustainability is here. And I'm a big fan of sustainability. I want to mention here, as we move forward with these energy storage or battery technologies, cost, sustainability, affordability will be the single dominant factor, because the market is expanding so rapidly, exponentially, I think. So demand will be going up. We cannot afford to use a lot of cobalt. It is a problem. We cannot afford to use nickel. It's a problem. So cost is a major driver. All along with the research in my group. So last in 2020, we were able to eliminate cobalt. That's the first thing. Cobalt is out. Then mined metal, get it out. Lithium, sulfur. All these I have mentioned here. My group is doing work. Lithium, sulfur. Then, so today cobalt is a problem. Cobalt is replaced by putting nickel. Tomorrow, nickel will be a problem. So you go to sulfur. Then day after tomorrow, lithium could also become a problem. So maybe you can use cobalt-free sodium ion batteries, particularly sodium sulfur. Both of them are plenty. All these Exxon, Mobil, Shell, or OMGC, they all have a lot of sulfur to throw away. There is a mountain of sulfur in Qatar, mountain. They want to throw away, or they want to get rid of. So sodium sulfur is actually my dream technology. Sodium is plenty, sulfur is plenty. There is no mining. You get sodium from seawater. That is the best technology for sustainability. You can also think of sodium organic batteries. We have done some work, but not too much. So the work in my group goes all the way from here to there, paying a lot of attention to the cost, sustainability, abundance, so that the poor countries can also make use of these technologies. So that's the goal. So this is kind of basic introduction to tell you. I hope at least you know the parameters we involved and the chemistry and physics involved. Now I'm going to show you more deeper. Maybe it's too much. Again, right now the cathodes used, positive electrodes used in the cell phone, laptop, electric vehicle, something called NMC cathode, nickel, manganese, cobalt. The question is, why do they use three metal ions rather than one? Again, if you want to go through that paper, that will tell you a lot of things. If any of you are teaching a class, that paper will be very useful. If you don't get it, send me an email. I'll send one. But like I said, Google, everybody gets it. I'm glad I published that in that journal. I was talking to the editor. Okay, Ram, why don't you write? It's okay. Wrote it, send it. Then it accepted. It was a very good article for teaching. Now, why they use three? Because each metal ion, there are several criteria here. This is also in that paper, several criteria here. If you look, that depends upon the band positions, physics, you should love it. The cobalt 3 plus 4 plus band overlaps with the top of the oxygen 2p band. So if I charge cobalt oxide more than 20%, I will not be not only oxidizing cobalt 3 plus to cobalt 4 plus, I will also oxidize oxide ion. That means I am creating holes. Physics, you love holes. You are oxidizing oxide ion by pulling out electrons. You create holes. So that will go to superoxide, peroxide, and oxygen will be released. So more than 50% of the capacity of cobalt oxide cannot be used. Limited capacity. Manganese, well above, you can use all the capacity. So chemical stability wise, manganese is the best. Cobalt is the worst. But there is another factor. When you charge, you pull out a lot of lithium from this layer, your cobalt or manganese, they are in this transition metal layer. When you pull out a lot of lithium here, there is less positive charge. So automatically, these ions will tend to fall from this 6-fold coordinated octahedral site through a neighboring 4-fold coordinated tetrahedral site to this. For that, one can calculate the crystal field stabilization energy. If there are chemists, you have Hughie book or Cotton and Wilkinson book, for example. Crystal field stabilization energy in the octahedral site, tetrahedral site, very simple calculation. If you do that, cobalt has all the 6 electrons in the low-lying T2G band. Therefore, it will not migrate from this layer to that layer. That is a gift. That's why cobalt was first used for commercialization. Manganese, very little stabilization in the octahedral site. Therefore, manganese will migrate from here to here. It will transform to another structure. Voltage will keep on decreasing during charge discharge. That's a problem. The good thing is, manganese is good here, manganese is bad here. These are the two important parameters. They are diametrically opposite. Cobalt is good for one thing, bad for another thing. If you take nickel, very nicely, it's in between all these manganese and cobalt in all these parameters. And nickel can also be oxidized all the way to 4 plus. You can get higher amount of energy stored. That's why all the action is on increasing the nickel to all the way LiNiO2. But it has cycle thermal air instability. So we have been trying to work on it to fix it. That's what we have been doing for the past few years, and we have been successful to eliminate cobalt. When we do research in my lab, I want to point out we have three good things. We make our own material consistently. This is a secondary particle, 12 micron. We can scale up 10 kilogram per batch, consistent, like any other big company makes in Korea or Japan or Europe or China, or better than that. One. Second, we make full pouch cells, so we have a good realistic assessment of the performance. Third, we have fantastic facilities set up at the University of Texas at Austin, surface characterization, bulk characterization, so that with that we have a good time. You see here, this is 33% nickel or 30% nickel. When you go to higher amount of nickel, 90%, capacity is increasing, but as you keep on cycling, the charge holding is decreasing, so that's the challenge. So how do we fix it? So this material, one material has 80% nickel, that's good. The one has 94% material, fading more. So we have been trying to understand using a lot of characterization techniques after cycling for 1,500 cycles. The material that has 94% nickel has cracked more compared to the other one. So that will enhance the surface reactivity of the electrolyte. That leads to a lot of surface degradation. So we use time-applied secondary ion mass spectrometry, a very nice method. You can map. It is very powerful. We were the first to exploit this to have a good understanding. A lot of papers came out of that. So by having good characterization, we have an understanding of the dynamics, what is going on between the electrode surface and the electrolyte, liquid electrolyte reaction. So that has helped us a lot to learn. So, okay, you have a problem, you are telling us the problem, how are you going to fix it? The same problematic material, you put 2% aluminum, then you can store, the cyclability becomes better, the voltage stability becomes better, because as soon as you put aluminum, metal dissolution is decreased. These metal transition metals dissolve, they go from the cathode to the anode, and they mess around the graphite anode. When we put aluminum, that is decreased, that's why you get better performance. So anytime we dope, we always get better cyclability, better safety, and better air storage stability. And why it is? This is good for physics people. You might have heard about, or you may be teaching, I don't know whether you teach or not, for your students, Anderson localization. If the electrons are very well, this is a Yertz-Shard octahedra. The metal ions see each other directly. The electron is very well delocalized. As soon as I put an aluminum or magnesium, they are inert. That electron delocalization is perturbed, so the band will narrow. It will introduce Anderson localization, impurity band. So because the band narrows, the covalent, the electron delocalization is decreased, and then that leads to less oxygen mobility and less electron mobility, so that decreases the metal dissolution. That's why we get better performance. I think it's too much detail, but at least I'm telling you how physics and chemistry will look to understand, to make better. Aluminum or any doping improves these materials. This is again air reactivity, simple treatment with the phosphoric acid, then you form Li3PO4. So we use powerful techniques. This is from a time-applied secondary ion mass spectrometry. You can dope with O18, oxygen 18 isotope in the cathode. Your electrolyte will be like regular oxygen. So you can find out the dynamics between the electrode and electrolyte. And we do a lot of TEM characterization. The material which is not surface coated, surface protected, has a lot of unwanted surface phase formation. If you coat it, then very little. So we have all these kind of analysis that is reflected in good cycle life for 1,000 cycles. If you protect it, the surface, if you don't protect, then it falls off. So I mentioned last 2020, we eliminated cobalt in the battery. 50% of the cost comes from cathode. 50% of the cost comes from cathode. So cathode is the most expensive. And in the cathode, cobalt is the most expensive. That's why cobalt has to be thrown away. In 2020, you were able to eliminate cobalt. When you see here, all of them have 90% nickel. NMA has no cobalt, 90% nickel, 5% manganese, 5% aluminum. All others have cobalt. The cobalt-free material shows performance as good as this gray colored. The cobalt as good as the cobalt-containing materials, or even better, some of them. And the safety is not compromised. Fast charging or charge rate is not compromised. So we have a startup out of my lab, the patent developed, that's in Houston. They are setting up a pilot plant to produce 150 tons of cobalt-free cathode for domestic supply as we move forward. So that's what that is. I talked about sulfur. It has 10 times more charge storage capacity, but sulfur is a poor electronic and ionic conductor, and you start with the 8-membered sulfur ring that is insoluble in the electrolyte. Once the ring breaks slowly, you get these species. They are soluble in the electrolyte, so they go from this electrode to that electrode. That is a big headache. That degrades the cyclability. Lithium metal gas. Talked about sulfur, mossy, dendrite kind of microstructure. So in the literature, what people do is throw a lot of liquid electrolyte so that you can overcome the poor ionic conductivity, put a lot of carbon so that you can overcome the poor electronic conductivity. That is okay, but that will result in pathetically low energy density, because you put a lot of carbon that's not doing anything there, that junk sitting there, a lot of electrolyte, salt and solvent, that will all bring down the energy density pathetically to maybe 50 kilowatt hour per kilogram. Whereas right now it is 250 with the lithium ion. So it will decrease very much down. So that's not good. So we have been controlling all these parameters as you see here: low carbon amount, high sulfur loading, so low liquid electrolyte, and low amount of lithium. We call it 5.5. Also, we do pouch cell. If you do button cell with lithium sulfur, it will not be realistic. It will not tell you everything. So we do pouch cell. And then we have done a lot of fundamental work to understand what is really going on. How can we suppress it with the molecular engineering by substituting tellurium? You can change the lithium deposition morphology from this ugly thing to this much more smoother, and that is also reflected in better cyclability. So this is again chemistry. If you do not put any tellurium, your cyclability is like this. As soon as you put 10% tellurium, it substitutes into those polysulfide to form lithium polytellurosulfide. That forms a nice protective layer on the lithium metal anode. Then that gives you good cyclability. Again, we can verify. When you have that, you do not have the oxidation of the sulfide species to sulfate species. When you have tellurium, you don't have, it's pretty fast oxidized. Again, using XPS, X-ray photoelectron spectroscopy, as well as time-applied secondary and mass spectroscopy, we have delineated what is really going on. Finally, sodium. Sulfur is my dream technology. Electrolyte is the major problem. Conventional electrolytes lead to a lot of gassing and safety problem and dendrite. We have used a localized high concentration electrolyte. That kind of gassing and dendrite is suppressed. And then the dynamics also changes. Usually with sulfur, as I mentioned earlier, it is a dissolution precipitation. Dissolves, solidifies. We change that to a quasi-solid state reaction, and that gives you this kind of performance. This is the best data available in the literature as far as sodium sulfur is concerned. So you see all the way from cobalt to pre-lithium ion cells, lithium sulfur cells, sodium sulfur cells, like I pointed out earlier, going all the way from that end to more and more sustainable technologies. So that's what we do in our lab. This is my last slide. Right now, the lithium ion energy density is 250 watt-hour per kilogram. Like I said, in the sulfur, if you throw a lot of liquid electrolyte or a lot of carbon, this number can go to 50 watt-hour per kilogram, for example. That is not good. So when you increase the nickel content, that number can go to 300 or 350. Instead of graphite anode, if you have lithium metal anode, that can go to 400 or 450. If you go to sulfur, maybe 500 watt-hour per kilogram doubled. And then if you go to sodium, all these numbers will be 50, approximately 50 less than the numbers you see here, analogous to that. If you go to all solid state, it could in principle give 500 watt-hour per kilogram or more, but only time will tell because of interfacial charge transfer problems and other things. So India, before I close, the battery technology involves 4 major steps. The material development, material design, that's what I talked about in my talk. That's just basic chemistry, physics, material science, the bottom. Next,